In the next subsection, I want to introduce a notion on strings that at first seems unrelated to our task, but it will be the key ingredient to a different way of string matching that then is more useful for parallel execution. And that's periodicity. So let's first start with the definition, and I'll walk you through the example then. If we're given a string, as always, and characters, then we say it has a period p, so p is a number, and it has a period p if for all positions, if you start at the ith position and you add p, you find the same character. All right. There's some boring consequences. P equals 0 is always a period, but none that tells us anything. And any number bigger than n is a period, just because then this for all statement is empty. This iterates over all numbers in this range, and if that range is empty, it's an empty statement. So again, these are technically fulfilling the definition, but we'll not really regard them as periods. They're trivial periods if you want. So we'll exclude those from the discussion. But strings can have non-trivial periods. And here's an example. So if you take this string written down here, and you take a copy of that, shift it over by 6 positions. So you match position 0, right? So let me maybe write down the indices just once. I know this is baby example. And up here as well. Then you see you match position 0 with position 6. That's a shift of 6. And if you do that, all the characters match up. And that's the condition that we need for a period. There's another string that has a smaller period. And so you see a small period means there's a lot of repetitiveness going on in the string. And in particular, we'll come back to this, but if this period is bigger than half of the string, then as in this picture, you have some overlap between prefix and suffix, but that's about it. If the period is substantially smaller, then you see there's a certain range, this ABA, that repeats over and over in this string. And we'll use this fact in a second. I want to connect this. If you've seen the picture on the previous slide, maybe this already sprang to your mind. We've seen something like this before, and indeed we have. So in other words, if you have a period and this p is the shortest, is the smallest number p that is a period apart from p equals 0, then this is also if you take the first n minus p characters, that's the longest prefix that is also a suffix of this string. So I guess we want to have the picture for this. If the minimal period is p, then that means if you take the first so and so many characters, they're down here, n minus p, that is also a suffix of this part. Okay, so this string here is our S0 up to n minus p. And this here is the suffix starting at p. Okay, sorry, this should be a little clearer because the square brackets are different. I guess I should have said here these are equal, right? What's also true is that the longest prefix that's also a suffix of s has length n minus p. And that's something I told you in the last unit. Please memorize. You remember the red box? That's exactly the failure function of the KMP algorithm. So in short, the statement here is, if a string has a minimal period p, then you can get this p from the last entry in the failure function. It's the failure link of the last state in the automaton. Okay. Just because if you had matched the entire pattern and you now find something you want to continue, you have to shift this over exactly as much as the period is. A second small observation about periods is this lemma. If you have a string that has two different periods, P and Q, and they're not too large, so their sum is less than n, then you also have a period for the greatest common divisor of the two. And for that, I just want to give you a proof by example. Now, this is not in general a valid proof. And the formal proof used to be part of the tutorials, but it was never really very insightful, and we're not using the lemma massively. That is. Okay, this is not working. Let's do it this way. So let me see. Might have made this a bit short. Let's do a small example. So let's suppose the string has period. It's boring. Let me make the example a little bigger. Otherwise, we don't see the interesting part of the statement. I want to have two numbers whose greatest common denominator divisor is not just 1, but also I need them to be in sum less than n. So the example has to be a little bigger. So let's take a period of 6. And so the implication here is these are all the same. Right? And suppose we have another one. So I'll just put this in the same as the other one. Let's say we also have a period of 4. Which first of all just means that these are the same. But of course, equality is transitive, so it's also these are the same. And so let's suppose we put an arbitrary letter in the first position. Say this is an A. Now, if that's an A, of course, this is the same A. And so by these equalities, it immediately implies that this is an A and this is an A. And look what happened. So if you put this A in the fourth position into this one, then you get an A here. So A also must be at the second position. And so you see, you can fill with these games, you can fill every other letter, which means that the string actually has a period too. So you can do the same if you put an arbitrary letter in the second position. It is inherited here and here, but also here because it's also the second position, so it gets into here and here. So that means it goes into the fourth position. So after fixing the two letters, the first two, the equalities that are implied by these two periods, 4 and 6, imply all the letters are filled. And that's another way of saying the period is 2. As I said, this is not a proper proof of this statement because it's only shown on this example. But that's the essence of what's happening. And I don't think the formal proof in this case is really insightful. So now, after introducing this idea of periods and the idea of shortest periods, and the previous lemma is just a cute way of finding the shortest period. You can try to look at the string and guess what periods you find. And if you found 2, you can always jump to their greatest common divisor and get a smaller period, potentially. So that's a way to find periods by hand. The important notion here now is that of a periodic string. And we call the string periodic if its smallest period is less than half of the string. And remember, that means you shift the string over by less than half of it. That means it has to repeat at least another time. Maybe repeat the little picture again, just conceptually. So suppose the period is like this. Then that breaks the string into these blocks. This must be the same as this because it's the same string. Oh, come on. And then because of equality, you have the same block here, and that copies to here. So the string consists of the same block repeated until at some point it stops in the middle of a repetition. And so we can say this is a case where S is highly repetitive. The more precise statement is stated here. S is determined by some smaller string of length p, and you keep repeating this until you filled enough characters. And the other case is an aperiodic string. And in a sense, the periodic strings, they're kind of redundant in that they are not really n characters worth. They're determined by much fewer characters. But the aperiodic strings cannot be written in this way. And so the formal definition is shortest period is bigger than n half. All right. Time to wake up and see if this notion is clear enough. So here's a string for you. Is that one periodic or not? Okay, 24. We get up to 30. Yeah, a couple of people still typing. All right, seems all done. I wanted to click on log. All right, in this case, it's not periodic, which might be surprising. The thing is, this string definitely looks boring, right? It has lots of repetition, but it's not periodic according to the definition we've just seen. And the reason is that if you take this string, many A's, but then a B at the end, there's no way you can overlap this with itself without creating this. Okay, I didn't switch the, thanks. So correct answer is no, as I said. The reason is that whenever you shift the string by any amount over to the try to overlap with itself, you will always place the B atop of an A. So you can never have this match. So what's the period, the shortest period of this string? It seems any P doesn't work, but there is always a shortest period, which is N. If you shift the string entirely behind itself, then by definition, it's a match because there's nothing to align anymore. So shortest period is N, which is definitely bigger than N half, and so it's aperiodic. So don't be tricked into thinking that periodic necessarily means repetitive and vice versa. It's not exactly the same. And indeed, this is a fairly restrictive and concrete notion, this periodic. All right.